Some more details about a few of the sandwich modules. As you can see, every of these 3 examples are equipped with a microcontroller. They are running at different clock rates. They only contain little flash memory, so there's not room for large programs. Some of them can have external RAM memory, some don't, like this one. And the idea behind the different sandwich modules was to get one sandwich module per interface or per purpose, and to give you like something like a toolbox where you can choose from and put the parts together that you need. Okay, so far for the hardware. Let's switch to the software part. First I want to start again with some related work. This related work was conducted by other research projects, and it already covered some of the aspects we are now combining in a different way in the Ambicomp project. At first, the Ambicomp system tries to provide a single system illusion. This is a concept that is already known from the field of supercomputing or cluster computing. A single system illusion, especially when implemented through a Java VM, is something that provides you with a platform where you can write applications for a multitude of computing nodes and write your application in the same way as you would do for a single multi-core processor. So you just use threads, and these threads are communicating with each other, and during the runtime of the Java VM, these threads migrate onto different nodes in the cluster. So, especially in the supercomputer field, you gain a speed up from executing the threads on different nodes. Another aspect, which is already being explored, is executing a Java virtual machine without any OS. Okay, we can skip that Squawk VM, I already mentioned it, it was the VM on the sunspots. And the third aspect is distribution of software modules. That may sound familiar to many of you. I want to mention here the concierge implementation. It's an OSGI implementation, especially suited for embedded systems, and remote OSGI, which is an extension to that system to distribute bundles in a small network. And it's running on platforms like Lego Mindstorms, for example, where you can easily distribute software modules between the little Lego robots and let work them together. Okay, what Ambicomp makes out of these aspects is we combine them in a different manner, and we are targeting much smaller hardware devices and a much larger scale of distributedness. By that I mean we probably will run on much more nodes than, for example, the Java VMs from this cluster field. Okay, more details to our Ambicomp virtual machine. At first, it runs on our controllers. It isn't supported by an operating system, and this core software part is the part that achieves the single system illusion. It runs completely decentralized and self-organizing. Okay, these are buzzwords, but let me explain it in a different way. Completely decentralized means that every microcontroller in the networks executes one instance of the Ambicomp virtual machine. And all instances of the VMs together make up this decentralized system. So you can deploy an application on one node and let it start, and deploy another application on another node and let it start. And there is some magic way between these nodes that they can share objects or other resources. I will explain that later on. of course, for this decentralized execution, we need code, object, and thread migration. And we are running on a multitude of sandwich modules, like I described before. We are using Eclipse for the development of our Ambicomp virtual machine itself. We are using CDT for that purpose, but we're also using Eclipse as a development tool for users of Ambicomp platform. As you can imagine, with the sparse resources on our sandwich modules, there has to be some magic, because your typical class files wouldn't fit in these few amounts of RAM. And we do a pre-processing step before deploying class files onto the nodes. We are using a transcoder, like you maybe know already from the Android platform. This is using the same technique to shrink class files and reduce redundancy incorporated in the class files, especially redundancy when you use multiple class files for one application. Okay, and the last, but I think worth mentioning part is the implicit communication. We are using a special routing algorithm developed in our group. It's called scalable source routing. This algorithm comes from the field of peer-to-peer systems and provides key-based routing. Key-based routing is a very simple semantic where you can put data into a network and the data will go to a specific node that is somehow near to the hash key of that data. So you always have one node or a few nodes responsible for some data. And with that semantic, you can very easily build a distributed hash table on top. And with a distributed hash table on top, you can find all kinds of objects in the network in a very easy way. Short overview about the stack we are using. You're already familiar now with most of the parts. On the bottom layer we have the hardware. Over the hardware there sits the BIOS, the bootloader section. We also have a BIOS implementation running on Linux, so our VM isn't only able to execute on these microcontrollers, but the same kind of VM is just compiled with another compiler running on Linux to emulate devices.